Hi everyone, my name is Jogi Emmanuel. Welcome back to the channel. In this video or in this series, I'll be showing you how to compute or how to find the equation of the tangent to a particular curve. Of course, when given a particular point to that particular curve, to be more precise, have a pen, have a calculator, and have a notebook, pen, so that you can take notes, and don't forget to subscribe to the channel so that you can get more of the content as we upload. But I want us to read what we have here so that we can be able to solve everything in the autonomous sense. Well, this is the part one of our series. I'm going to be reading some few notes here which I've compiled, guys, for you. So we are working largely on what? On finding the equation of the tangent to a particular curve. Of course, when given a particular point to that particular curve or a polynomial, just to be more precise to that one. Well, I wanted to define what is a tangent first before we get, or before we dive, in fact, to the whole series. A tangent is defined as a straight line that touches the curve or a graph or a polynomial at one point only. All right. So a tangent is a straight line or it's a linear function that touches or that cuts the not to cut but to touch. Get that concept right, to touch at a particular point only. So we've got the most popular general equation of the tangent, which is going to be given by this one. I'm going to highlight it for you. This one is the most popular general equation of the tangent line, which is going to be given by y equals to mx plus c. We know it from analytical geometry, in fact, so we're not surprised to see that. Well, it is another point here to note: the gradient of the tangent is equal to the gradient of the graph at the point of contact. Therefore, the derivative of the graph at the point of contact is equal to the gradient of the tangent. All right, so I have two curves here to really demonstrate what is a tangent and what is a point of contact and what is a curve. So a curve normally is a polynomial. It's a function which will be given in most of the time. It's a function of x, in fact. So I have this curve here. You can see that at this particular point, let me highlight it with my marker here. So at this particular point, let me just do it like this. At this point here, okay, let me just change the color. At this point right here, we're going to call that point the point of contact. This is where the tangent line, the blue line right there, this is where it touches the curve at that particular point. And we also have the cubic graph here, which is going to be seen at this point here. It's going to touch the graph there at P and also at Q. So we have two tangents here drawn at P and Q. Those points, they demonstrate at P and Q, in fact, they define the point of contact at that particular curve. The curve in this case, we're talking about this cubic function, which you guys, I presume you know this is a cubic function in that view. So now what we also have here is that we need to define, you need to know how to define, in fact, what's a tangent. So I've defined it for you. You can go through that. What I want to explain here more precisely is the steps on finding the equation of the tangent line. So these are the steps. Suppose you are asked to find the tangent line for a particular curve or a particular function f at x at a given point. So here we're going to give you a point, x is equals to something. It's a point, you know, at a particular curve and at the tangent, where in fact the tangent touches the curve. That point, it's x is equal to something, which you also need to find the corresponding y value at that point. So I'll show you how you get that. So here is a step-by-step approach. Number one, you need to find the derivative of that particular curve. Remember that the curve is a function. So we need to find the derivative of that particular curve. It's the step number one that you guys should do. Number two, you need to plug or substitute the x value which will be given. This x is it's at a point you will be given. It's a point, x is equal to something. So you need to substitute this value into what? Into the derivative to get what? To get m, where m is defined as what? As a gradient of that particular a tangent line to the curve. Get that? Number three, if not already given in the problem, find the y coordinate of the point. How do you do that? You substitute the given x coordinate to the given curve. The curve is a function. Get that? It's a polynomial. You will be given that particular curve. So you'll be given a curve and a point. So you need to substitute it into the given polynomial to get the corresponding y value at that particular point of contact, And then now when you are done doing that, you need to get the equation of the tangent, because you'll be having the point, from the third step, and also you'll be having the gradient from where? From the second point. So now you have the gradient, you also have a point. So you can find the value of c, which we normally call it the y-cut of a particular straight line or a particular tangent. If it's a tangent to the curve, get that? Well, we also have the horizontal tangent, which is this one right here in blue. I'm just gonna try and show you this line here in blue. It's called horizontal tangent to the curve. What it means there is that the gradient is going to be equal to the derivative of the curve, and both of them, they are going to be equals to 0. The gradient of the horizontal tangent to the curve is going to be equals to the derivative of that particular curve, and both of them are going to be equals to 0. Please also get that. So now we're also going to have some few points here, which I'm saying that at a given point on the curve, the gradient of the curve is equal to the gradient of the tangent to the curve, which I've explained that earlier on in the second plot of my below the tangent definition. Well, the most important stuff also to note here is that the normal to the curve is the line perpendicular to the tangent at a given point. So what do we know about the relationship between, let me highlight that. I'm just going to highlight that for you. I'm saying right here, the normal to the curve or to a curve is the line perpendicular to the tangent to the curve at a given point. So here we are basically saying that the term perpendicular simply means that when you multiply the gradient of the tangent with the gradient of the normal, that must always give you the negative one. That you should know also from analytical geometry problem. I will also demonstrate. There are some questions which I'm going to demonstrate with you that how you guys see the relationship between the normal in the tangent to a particular curve drawn together, or when given the normal, you need to find the tangent, or when given the tangent, you need to find the normal, or when given both normal and the tangent, you need to find the curve itself. That I'm going to explain in my maybe next series or fourth series, I don't know. But now I want us to work largely on the basic stuff so that you get the whole idea as to what is the tangent line to the curve. Now I have an example one which I'm going to work now with you guys. So now I want us to pay attention to what we are given right here and answer the question in the autonomous sense. Now we are saying that example one, determine the equation of the tangent to the curve defined by that. So now the curve is defined to you. The curve is, I'm gonna do it like this. I'm gonna copy the curve. So the curve is f at x, which is given by 2x all squared minus 3x plus 1. What we know about the curve is that it is a special name called quadratic function. So it's a quadratic curve, to be more precise on that one. This is a quadratic polynomial at a particular point, which I was telling you that you must be given a point. So the point in this case, it's what? It's at x. It's at x is equals to a -1. So I want us to be more precise on this one. Let us check the step number 1 to find that equation of the tangent. We need to find the derivative. Now I'm going to do that with you. Number 1, we need to find f prime at x, which we know how to derive that from a differential calculus, and then that gives us a 4x and then minus a 3. This is the derivative of that particular curve. And then secondly, we need to get the gradient. How do we get the gradient? We say, well, the gradient equals to the derivative of the curve at a particular point. So the point now is what? Is -1. You are given that point. This is the point which you are given, beautiful people. So now how do we do that? We now substitute -1 into the derivative. So this will be 4 into -1 minus 3. Then this leaves us with the gradient of what? Of -7. If you punch that in a calculator, you're going to get that. Then thirdly, what are we looking for? We're looking for the corresponding y value of the point of contact when given the x coordinate of that. How do we do that? We say, well, remember that we do have got the formula that we know in function, that y equals to f at x. This in function, it plays a larger role, and I presume that most students know this equation. So this x, in fact, is this x, let me highlight it. This x right here, it's basically the input of that particular x at a point of contact. So I'm going to substitute that x of -1 into the curve itself, because this is the curve. It's not the f prime, it's the curve itself. So I'm going to substitute that point of -1 into the curve itself. So this will be equals to 2 of what? Of -1 to the power 2, -3 of -1, and then I'm going to write a +1. This will leave me with what? I have to be careful with that. It's going to be +2, +5, and +3, which is going to leave me with 5 plus 1. This is +6 in total. So therefore, we have got the point P. The point P normally represents the contact point. In this case, it's what? It's -1, the x value, which we're given right there in the equation. It corresponds with what? It corresponds with +6. So this is a point. I'm going to highlight it for you. This is a point, beautiful people. This is a point, and also this is a gradient. So, well, like I said, we have the most popular equation of the tangent, which is given by y equals to mx plus c, where m is a gradient, and y and the x is the point, is the point of contact, or is the point that lies within that particular tangent. You know, so in this case, the point of contact lies within the tangent line, and also lies, in fact, at the curve itself. So I'm going to use this point which I have found in this case. So I'm going to say, well, therefore, the y value here, it is 6, and then the gradient is m. I found in the second bullet right here. So the gradient, it is -7 right there, and then x is what? X is -1, and then plus c. Now this would give me the value of c. So the value of c, I don't know. Let's try and punch that into a calculator, and then this will be +7. We transpose that, will leave you with -1. So therefore, the equation of the tangent to the curve at that point of x equal to -1 is going to be given by the gradient of -7 multiplied by x plus the value of c, which at this point in time is what? Is -1, which we found that. So I'm going to highlight that for you. So this is the answer